Okay, so we are in Statistical Rethinking, second edition, chapter 14, and we're on question 14H4. And I think this and the final two questions all deal with the same data set, so this will be the opening of kind of a series of them here. So what we were supposed to do is to look at a data set called Oxboys, which is a bunch of height measurements of boys at a Oxford boys club or something, and they had measurements taken at different ages, 9 different ages. And so we are going to try to fit a model of height on age. So now the question points something out that maybe is worth mentioning here verbally. But what we have here then is what's called time series data, where we have, multiple measurements across time of, the same subject, right? In this case, the height measurements of the same boy, and over many boys. So because each boy is going to have, their own unique set of factors that makes them a certain height and grow at a certain rate over age, we should really consider using our varying effects models for these types of things. Okay, and so that's what we're doing here. Okay, so so we'll get the data together, all right, and it looks like this. So we have subject, age, height, and occasion. I'm not sure what occasion means, and there's no data file on this, but I don't think that we need it, so we can just ignore it. Also notice that age here, it mentions this in the question, but age is, right, there's no such thing as -1 age, so what's going on here? So these are standardized values, and each boy is standardized by themselves, okay? So in other words, there's a chance that each of these boys are being measured at, different, intervals, different windows of their life. And so, the average of the measurements at which, a boy was measured is 0, and, I hope that makes sense. Now, the next thing that we do is we need to package all of this into a list. Okay, so here's my data list. So I'm not sure, I didn't look, if all of this, if the subject integers are sequential completely from 1 to 26, but just to make sure, I first turn that thing into, so it's already an integer, but there's a chance that it skips one of the integers, and then that will throw problems of Stan. And so first I made it a factor, and then converted it back to an integer, and so that should take care of that. And we'll get into the model here in a second, but I've also added the mean height here as well as part of the data. This is actually going to inform the prior, which I know you're not supposed to use priors for defining your. You're not supposed to use your data to define priors, but in this case, I believe that it's harmless because the things that we're interested in is the subject-specific effects and not necessarily, the global effects. And so the mean height across all measurements, it's kind of a global measurement. Okay, so here's our model. So we're modeling height as a normal distribution with mean mu and sigma, or standard deviation sigma. Okay. So here's the prior for sigma, and then mu is a linear model. And so I've broken this down into global parameters, an intercept, and a slope for age, as well as subject-specific parameters, subject-specific intercept, subject-specific slope for age. Okay, and then the parameters, the subject-specific parameters, are being wrapped up into a multivariate normal distribution here, just like we've done previously. That makes sense, right? Because it may be the case, right, that taller boys at any particular age are are taller because they're growing faster, or it could be that a tall boy at one age grows slower because they've already gone through much of their growth, right? So in other words, we might expect these two parameters to be related. Okay. So I've already ran this model, so we don't need to sit here and watch it go. Now, what we'll do is try to find how much variation is coming from the random intercepts as well as from the slopes. And so the way that I've done this is I've created normal distributions for each subject that came from the posterior distribution for the, in this case, the intercept for each subject. Okay, right. So maybe I'll just show this right here. Right. So for each subject, this is the pricey output, and I'm just grabbing the mean and standard deviation, and then with each mean and standard deviation for each subject, I am generating a random, normal. I'm generating samples from a normal distribution using their specific mean and standard deviation, and then I'm just taking the standard deviation across all of those samples. Okay. So and when we do that, we get a value. Okay. And now we'll do the same for the slopes, but the slopes are a little bit different, right? Because the amount by which the slope is contributing to mu here has to be multiplied by the age. And so to compensate for that, I am multiplying, I'm doing the same thing, but there's another step where I'm multiplying these samples by the average age across all data. Okay. But when we do that, we get a value, again, for the standard deviation. You see that the variation caused by the intercepts is much more than caused by the slopes here. Okay. And so we can actually kind of maybe confirm this by plotting. So this is the growth of each boy. Okay. And if you look at the intercept, or in other words, you can just look at kind of the spread at any vertical column of heights here, right? You have however much spread. Okay, so here it looks to be maybe you go from maybe 130 to 165 or something like that. So call it 35. But now just kind of compare that to how similar the slopes are. Okay, the slopes are all very similar, whereas the intercepts seem very, very different, right? So the conclusion there would be is that the intercepts are in fact, causing more variability to height than are the subject-specific slopes. Okay, call that good.